The most commonly applied element to the concept of hybridization is carbon. And I'm going to explain to you a couple things that hydrocarbons love to do. So this is all of these are tetrahedral, so all of these bond angles are 109.5, so they're not 90 degrees like you look like it is on the paper. This is ethane. These are all tetrahedrons. So let's talk about these carbons. So I'm going to ignore the core electrons, which are the 1s electrons, because they're not available for bonding. They're core electrons. So carbon has 4 valence electrons, so we're only focusing on the valence shell. It has 2s and 2p electrons. So these are supposed to represent orbitals. The arrows represent the electrons. They are pointing in opposite directions because of Pauli exclusion principle, stating that they need to have opposite spins in order to be in the same orbital. I put my p electrons like this because of Hund's rule, meaning it's a lower energy configuration. If it was really like this, though, carbon would only form 2 bonds, but we know that's not true. So what happens is, to prepare for bonding, a little bit of energy is needed, and we do what's called promoting. We promote one of those electrons, so each of the orbitals is singly occupied, like such. But if this were the real case, this would mean that one of the bonds with the s electron would have less energy than the one with the p electron, resulting in a different bond length. But we see that that is not the case. All of the electrons have equal energy, equal bond lengths, and equal bond angles. So what we call this is that 1s and the 3p electrons will do what's called hybridization. So this is the Sp3 hybridized orbital. Let me draw you a picture of what we're talking about. We label these types of bonds are called sigma bonds. So single bonds are called sigma bonds. So each carbon has 1, 2, 3, 4 sigma bonds or 4 single bonds. And notice that 1s and 3p electrons had to hybridize. So if you count those superscripts, it'll add up to the number of sigma bonds. Let me draw you a picture of that. Remember our 4 orbitals like such? When you have a sigma bond, it is a head-to-head bond like such. And this area right here is your head-to-head sigma bond. These on the other side will also form 4 other single sigma bonds with the hydrogens right here. So both of these carbons are said to be Sp3 hybridized because I needed 4 electrons to have equal energy. This compound is called ethene. It's one of the compounds that they can use to ripen bananas. So when they pick bananas, they're always green. And then when they're shipping them over, they pump ethene into the container. Ethene or ethane, and it speeds up the ripening process. Otherwise, what would happen is bananas would spoil before they ever got ripe. So we kind of got to help them along. If anybody's a biology buff, reading up on bananas is actually kind of interesting because they're not really a traditional plant. Each banana that you eat is a clone of the other bananas. So the problem with that is they're all genetically identical, meaning that if a fungus or something like that comes through, it wipes out all of them. So that's already happened once. All the bananas that people used to eat in the 60s were called Big Mike. Yeah, I don't know who named them. But then a fungus came through and wiped out all the bananas. So they had to come up with another variety, which is what we eat now, which is called Cavendish. But don't panic, though. There's a virus spreading right now in bananas. Have you noticed you can't get bananas, really, like you used to? Well, it is spreading, but they're fast at work trying to come up with another variety of bananas. So, did you know you've never actually seen a banana? Anyway, I digress. Okay, so in this case, let's get ourselves prepared for bonding. In this case, we don't have 4 sigma bonds. This double bond is the combination of 1 sigma and 1 pi bond. So each carbon in this particular circumstance has 3 sigma and 1 pi bond. So only 3 of these electrons need to hybridize. These bond angles here are 120. So let's hybridize these 3 electrons here to be the same energy. And as you can guess, this is sp2. So what that means is you've got that one head-to-head sigma bond. But other bonds are going to be side to side like this. This is how we represent a pi bond. And this is our sigma bond here. So they're different kinds of bonds. And as you know, double bonds have more energy and they have a shorter bond length, because the p electrons that didn't hybridize have more energy. So all compounds that have 3 sigma bonds and 1 pi bond are going to be called sp2 hybridized. This is called ethine, 180 degrees. The YNE at the end tells us it's a triple bond. A triple bond, I'm sure you already figured out, is going to consist of 2 pi bonds and 1 sigma bond. So this time, we're going to have 1 S and 1 P hybridize. Like that. And they're going to form 2 pi bonds and 1 sigma bond here. So this is our sigma, and here's our 2 pi's. So 2 side-to-side bonds and 1 head-on bond. This is called sp hybridization. So let's summarize. A sigma bond is a head-to-head bond. Pi bond is side-to-side bond with those p electrons. So if you have 4 sigma bonds, it is Sp3, 1 S and 3 Ps, hybridized. If you have 3 sigma and 1 pi, this is Sp2 hybridized, and that's your double bond. If you have 2 sigma and 2 pi, it is Sp hybridized. So this is going to tell us single, double, triple. Now I'm going to caveat that you might hear somebody talking about dehybridization at some point in time, like if you go to search for videos or end up in somebody else's class. There used to be dehybrid. So we learned this is all for 4 bonds, 4 electron domains, right? So it's all for tetrahedral stuff going on. But we also learned about bipyramidal and octahedral. Well, that would need access to the D sublevel. Remember that you cannot exceed the octet rule for anything that doesn't have access to a D sublevel. So anybody in family in period 2 cannot exceed the octet rule because there's no access to a D orbital. So the bipyramidal ones with 5 electron domains used to be D Sp3 hybridized. The octahedral ones with 6 electron domains used to be D2 Sp3. So if you hear that or if you go to watch videos, just know that that's not going to be on the AP exam because they actually found evidence that that was not the case.